Okay, let's get started here. So assignment number 1 is due on Friday at noon. Just as a reminder, please email to me your finished assignment. Put the names of the group members and the actual file name. Also, if you are working in a group, you only need to turn in one assignment per group. After I expect an email back from me to confirm that I received it. If you don't receive that confirmation, you should contact me as soon as possible. Okay, because that means I might not got it. Obviously, though, wait more than 1 minute before you email me back and say, "Hey, did you get it?" So just be patient. I'm in meetings a lot tomorrow, so I might not be able to. If you turn it in like right about noon, I might not be able to get back to you until late afternoon or in the evening. Okay, so also assignment number 2, it will be likely out this weekend. So if you want to get started on it, check my website. It probably will be out there this weekend. And we'll start talking about assignment number 2 during our next class. So today we will finish up the graphics section, and then we will talk about some of the finer points of using a data step. Are there any questions before we get started here? Okay. So we left off on page 17. And we have a few more plots to talk about. The code for these plots is not in my notes, but they are in the programs. Also, these programs, as I mentioned before, contain a number of other plots. You are responsible for those plots that are given in the programs as well. Excuse me. Okay, so let's first take a look at this simple plot here. This is a histogram of the college GPAs in our GPA data set. We only have 20 observations overall, so a histogram's not necessarily that good of a portrayal of the distribution in terms of if you want to know the shape of it. But it provides a simple data set for us to work with here rather than me introducing you to another data set. Also on this histogram, we have a normal density drawn. The normal density is, and this is the default in SAS, is drawn with the observed mean and observed standard deviation as the true mean and true standard deviation for that normal density. The y-axis of this plot is adjusted, so it's not necessarily, let's say, counts that you would expect normally in a histogram. It's adjusted so that both the density and the histogram can be on the same scale, same y-axis scale. Okay, so let's talk about how we can do this plot in SAS. Let's see here. My programs are tucked away. Oh. Let me just clear some stuff out. Read in the data set once again. Okay, so the procedure that does this is proc sgplot. My data is in set 1. As you might expect for a statement to tell SAS, hey, I want a histogram, guess what? We have a statement called histogram. So I say histogram college. Now, if you notice on the plot, so I have kind of a blue fill for those bars on the plot. And I have lines outlining where the bars are. And this is the default. Why is it the default? Well, because if you notice, you don't see any options after the variable that I specify that I'm plotting. So let's say if I wanted to change, let's say, the color of that fill there from, it was like a light blue to red. Any thoughts about how one would do that?
That'd be the fill attributes.
Exactly. So, last time we saw a lot of options that often had the word like attribute in it. It was ATTRS abbreviated. We saw a variety of them, and there happens to be one called fill. So, for example, I can do a slash since I have an option. Fill ATTRS. Although I have a feeling yeah. Is that right? There we go. So how do I know I got the right keyword? Notice how now it becomes blue. It wasn't blue until I had spelled it right. And then I have equal. What do you think I would need to do after that to get a color fill of red? Any thoughts? Obviously, you could look at the help, type red. So just red, like that. You might be thinking that there's probably more than one kind of attribute that you could have for that fill. So if there's more than one, let's look at what we've done in the past. Notice how we often use like a little parentheses. So that was for line attributes. We had little parentheses there. So maybe we want to specify a parentheses and also specify color. Look in the help for other attributes that you could change as well. So we'll run that shortly. Also, you can look in the help for other options that you can do with these. So, for example, if I did not want to fill at all, I could just simply say no fill as an option. Now, to get the normal distribution or normal density on that plot, guess what? I have a statement called density. I want the density with respect to the college variable. And then I have a variety of options, such as, well, what kind of density do I want to put there? Type equal normal. It seems to make sense. And then if I want to have a nice little legend label that I chose myself, I have a legend label option as well. So let's go ahead and run this. And there you can see the plot. And again, sorry if I'm repeating myself, the way to better understand how SAS works is to, go to the help, look at the various options that you have, and try them out. See what happens. What's the worst that can happen to you? If you try it out, it doesn't work. Okay, big deal. Maybe you could figure out then, that would be good practice then to figure out, well, how do I solve that problem, that it didn't work? Or maybe in the end that option wouldn't make sense for a particular kind of plot, so that's why it didn't work. This is where you can look at the log file or the log window to help you understand what's going on. Any questions about this plot? Okay, let's go to the next one. So we've got some box plots. So just to review what box plots are. On the y-axis, and this is now for the serial data, y-axis I have sugar, x-axis I have the shelf number. And let's just go through the review. So let me get my pen out. So this line, let me draw this in red. This line right here, what does that represent on a box plot? Is that the third quartile? Median. Yep, median. Third quartile is up here, so people call it Q3. What's this one down here? Where's that drawn at, I should say, relative to the y-axis? Sorry if I wasn't specific. Q1. And what are these things called that are extending out? Yep, the whiskers. And how far are they extended out to?
The range.
Not necessarily 25%. Within the data set? So you got to be very careful here with how box plots are drawn at this portion in terms of how far is this drawn out. And unfortunately, I had a note here, in my notes here, how far does SAS draw out those whiskers? I forgot to check that before class. I apologize. It's different based upon software, and often you have various options that you can use to get these differences done. Unfortunately, there's just not a standard. I believe off the top of my head what SAS is doing is actually drawing these lines here out to the min and the max. Okay. Another very common way of drawing these out would be, let's take this one here, Q3 plus Q3 minus Q1. Does anyone know what this is? In interquartile range. And then this is multiplied by 1.5. So that's another way that these box plots are produced. And to make it even more confusing, sometimes software packages will either pick the largest observation that is less than this but greater than Q3, or it will actually draw it out to this value if there's an observation that's greater than it. And how are those observations often denoted on plots? You might have some circles out there, and those are often referred to as outliers. So I apologize, I don't remember exactly, or I'm not 100% sure exactly how SAS is drawing this out. But I believe what it's doing is actually going to the min and the max. And the reason why I say that will be clear based on the next plot. But this is a good chance for you to investigate on your own how this is done. How would you do it? Well, simply do the calculation of the Q3 to Q1 and see what the value is compared to what you see on the plot. Also, what could you do? Maybe add an outlier to the data set. Let's say a college GPA, oh, I'm sorry, we're dealing with sugar. How about sugar equal 1? Eat pure sugar for your cereal. Do a sugar equal 1. That's an outlier. See how SAS reacts. Just add it to the data set. And that's how you can figure out how this is actually done. It should also be given in the SAS help too, although I don't remember off the top of my head if I've seen it in the SAS help. Okay. Oh, what's this point right here? What do you think? What's that? Mean. Yeah, that's the mean. Not all box plots have the mean drawn on it. One advantage of doing that is that you get a little bit of a measure of skewness. Because let's say if you have a distribution that's right skewed. So let's say my distribution looks like this. Notice how it's right skewed. Is the mean going to be greater than or less than the median? What do you think? The mean is going to be greater because on that right tail of that distribution, you're going to have some larger observations. Which is more sensitive to larger observations, the mean or the median? The mean. The mean is going to be more effective. If that's not clear, try it on a data set. Create your own data set. See what happens. When you, let's say, adjust one observation and make it a lot larger. See what happens to the mean. See what happens to the median. Okay. So here's my plot. So relative to our original, let's say, research hypothesis that we had, what do you see in this plot? What's happening here? We hypothesized that something was happening with sugar.
Shelf 2 has more sugar.
Yeah, shelf 2 seems to have more sugar. But the key is here, compared to what we've seen before when we were just simply calculating mean, we see a distributional shift. That's the key. That's the key. Also, I'm interested in this, right here. Notice how mean and median are quite different. Let's talk more about that in the next plot. Okay. So when I see something like this, this intuitively is starting to make me think, hey, maybe something's going on with shelf 2 compared to the other shelves. Because it's actual distributional shift. Let's see here. So let's take a look how we can do the plot. I need to get my data into SAS again. Unfortunately, both my serial data set or my serial programs and my GPA programs both have a set 1. And so that makes it a little bit more difficult when going back and forth between the two data sets. Okay. Yes. Okay. So box plots. Again, proc SG plot. As you might expect, there's like a box option, but you could have boxes that are vertical, like what we just had, or horizontal. So there's a V box option and there's an H box option. I chose the V box option because often the response is what's located on the y-axis, and you can think of sugar here maybe as our response. And also, I specify sugar. Then I have some options here. Suppose I do group equals shelf. Well, the data is grouped by shelf. That makes sense. And then this is the first time where I think this is the first time where I've shown you how can you change the label on the x and the y axis from the default. The default is just simply the variable name. I did the variable name here, variable names, but I capitalized the first letter. Obviously, in other situations, you could be more descriptive. This works here. Let's see what happens. Well, isn't that kind of pretty? Everything's different colors. Is that really adding really much meaning to the plot? No. And so, when I was first doing this plot, I did this. I was like, well, that's kind of disappointing. Why do I need why do I even need a legend? Why can't we just label the x-axis by shelf 1, shelf 2, and so on? And so, well, how can you do that? Well, instead of what might be intuitive of using a group option, there's a category option. So if I do that, then we get the plot that's in minutes. Any questions? Now, whenever I do a box plot, I always add an additional part to it, except for in some unusual situations. But I almost always add a part to it, and that is I actually do a dot plot on top of it. So here's actually the plot in R. The red circles are the actual observations. Now, why do I do that? Well, because the box plot isn't giving you all the information that you would like. I like to know what the actual observations are if I could. And so that's what I've done here. Okay, let's talk about this. So for example, you see where my mouse is here? Notice how right down here, shelf 3, I have a little red dot there. So what that represents is that there's some cereal in shelf 3 that has very, very little sugar. In fact, there's one cereal on shelf 3 that has no sugar at all. Now you might be wondering, well, why are these points kind of moving about relative to that x-axis? Does anyone know what I've done to these points? There's a statistical term. I have jittered the points, J-I-T-T-E-R. I have jittered the points, meaning I have moved them in a horizontal manner randomly to avoid overlapping. So, for example, you can see here we have some points that would have been overlapped, but because of the jittering, they are not overlapping. They have the same y values, but they don't have the exact same x values. But but with respect to how I jitter, notice I don't move them that much in the horizontal direction, so that I still know, okay, all these points are relative to shelf 1, all these points are relative to shelf 2, and so on. So jittering is a very nice technique to help avoid overlapping. It's not completely perfect. If you're not careful, right here, you notice, you might think of that as one observation, but it's actually 2. Okay. So, what else is gained by looking at this dot plot here with the box plot? You see anything that pops out to you?
You can see where that median for 1 is so high.
Exactly. So we essentially have what's often referred to as a bimodal distribution for shelf 1. Now remember, my original research hypothesis, which was the lower shelves are going to have the higher sugar content cereals, so kids like my son Callum can grab them easily. And in that video for Callum, obviously the second shelf, but you would think also the first shelf too. And so what we're seeing here is bimodal distribution. We do have some of those high sugar content cereals on shelf 1, just like what we have for shelf 2. But for some reason, we also have some very low sugar content cereals. So that that should pique your curiosity and make you want to investigate. Well, what are these cereals? And maybe one can come up with a conclusion of, well, why are some very low sugar content cereals on that bottom shelf? You can investigate that on your own. So also what we see here too is you have some information about, well, how R in this particular case is actually doing the plot. Notice always at the end of the whiskers, you always see an observation. Now how is R actually doing these plots? They are doing what I had said here with the more complicated version. They are using that as the top in terms of where that top line goes to, except when an observation doesn't go that far, then they will lower that bar to where that top observation fits within Q3 and that top range there. That can be kind of confusing. Does anybody want me to repeat that? I think the answer is no. Did you want me to repeat it? Okay, I wasn't sure if that was like that or not. Okay. So, the top bar is drawn at this. Except if the largest observation is less than that. And so that top bar will be lowered to that smaller observation. If the largest observation is greater than that, then you will see that represented on the plot as an outlier. A similar way of drawing the bottom bar is done as well. Is that clear? Okay. So now that I'm thinking about this more as we go along, I wouldn't be surprised if that's what SAS is actually doing. Because you'll notice here's the actual dot plot that I do in SAS. Fortunately, it's a lot more difficult to overlay in SAS, which is a great example of why R's graphic system is better than SAS, better than SAS is, even after SAS has made some improvements. But you'll notice that where these bottom, where the lowest dot, the highest dot or circle are represented in this plot match up with where you see the top and the lower bars on that box plot. In the end, knowing exactly how these box plots are drawn is kind of boring, but you need to know. It's just you have to understand what the plot's giving you. So anyway, so now here is the actual dot plot. And so if I were to do this in SAS, I'm going to use proc sgplot. What do you think the statement's going to be to do this? I'm sure all of you are not wanting to respond because either it's too easy or Chris is asking a trick question. Well, Chris is asking a trick question. You would think it would be dot. In fact, there is a dot statement, but dot will not produce a plot like this. Try it and you'll see what happens. I think there's an example in the program. And instead, what I actually had to do was kind of manually construct the dot plot by using a scatter plot, where my y-axis value was the sugar, and the x-axis value was the shelf number, and then I jittered. So this is how I do it. There we go. So sgplot, I'm doing a scatter plot, x-axis shelf, y-axis sugar. option, jitter. How much do I want to jitter by? Well, I'm going to move every observation by at most 0.2 from where it originally was. And this is 0.1, let's say 0.1 above or minus or 0.1 below. So if the value is, if the shelf is 1, you're going to have points between 0.9 and 1.1. Okay? And it's just randomly moved. Again, I have a y-axis label, and then this is the first time, and I do this for demonstration purposes, but this is the first time how I show you how you can actually control what values are being plotted on the x-axis in terms of your tick marks, for example, and how they're labeled. I'm going to put values of 1 to 4 by 1. If you want to know more about minor tick marks, let's say for some reason you wanted a tick mark at 1.5, or maybe 1.1 to 1.9 by 0.1, I give some information about how to do that there. All this is helpful to know when you really want to have absolute control of your plots, and very often that's what you do want to know. You don't want to just work with the default. And so in the end, this is my plot here. Notice the jittering there. As I said, points are randomly moved. If I were to rerun this code, I get the exact same random movement in the x-axis direction. So it's not as random as you might expect. In R, when I do this, it does change. The plot will change every time you run it, unless you control how that randomness is done. Okay, so that's the end of those plots. Are there any questions? Well, let's say, especially like for an assignment, but maybe let's say you are writing up a report for another class. Let's say you want to take this plot and put it into Word. How would you do that? Well, I can right-click on it. I can say copy, come over here to Word. Oops, no, I don't want to get my email out. Go away. I go over here to Word. And as you might expect, I can just paste. And there's my plot. Not difficult at all. Let's say I wanted to save this plot for some reason to a file. I can right-click on it, save picture as, and I recommend going with the .png option. That would be the best quality for what you can do. You only have PNG in a bitmap option. Alternatively, what you can do too is what's demonstrated in the notes. The highest quality way to include a plot in an actual document is to export that plot out as a PDF file. That will be the highest quality. So, like for example, whenever I actually write a paper for a journal, they want to have the highest quality possible. I always use a PDF file, or actually a PostScript file will do it too. But I think PDF is fine. So how can I get a PDF file out? Well, I think the best way is just simply use some code. So let's say in here I have my proc sgplot code. Around that sgplot code, I can give an ODS statement, which says, okay, this is what I want my output to look like, or in this case, where do I want my output to go to? I want it to go to not to the results viewer, but to a PDF file. And then I specify a particular location on my hard drive where that PDF file is. When I am done doing this, I need to actually tell SAS to close it out. You're done. And that will produce a very high quality image. Let's talk briefly about something called Trellis Graphics. In Stat 873, multivariate methods, I spent a lot of time talking about Trellis Graphics because these are a cool way to do plots when you have multivariate data. Multivariate meaning you're plotting, let's say, well, I guess more than one variable, but let's say if you're plotting 3 variables, 4 variables, 5 variables, and so on. Trellis plots came out in the early 1990s. They're very useful in terms of what they basically do is you can imagine a situation where you have, let's say, 3 variables. And you want to do a scatter plot between 2 of the variables. Well, what are you going to do with that 3rd variable? And what Trellis plots allow you to do is condition on values of that 3rd variable so that you could have, let's say, one scatter plot here where you condition on a value of that 3rd variable between, let's say, 0 to 1. So all observations that have 3rd variable 0 to 1, here's a scatter plot for variable 1, variable 2. Then let's say variable 3 somewhere between a value of 1 to 2. Let's do a scatter plot variable 1 and variable 2. And these plots then, these individual plots, which are called panels, are laid out in a trellis-like fashion, where you have rows and columns to that. One of the most famous examples of this is this particular plot right here that was often used to describe what trellis plots are. And real briefly, what we have here on the x-axis is we have different kinds of barley. On the y-axis, we have different kinds of barley. On the x-axis, we have barley yield. And the light blue dot represents the 1932 yield. The kind of a reddish dot denotes the 1931 yield. And so we can see, like, and so what was actually conditioned on was location. So that's the 3rd variable. And we can see that 1932 was not as good as 1931 for almost every single location except for, and these are locations in Minnesota, except for Morris. Something was going on in Morris. And nobody really noticed that until this plot was first done in the early 1990s. And as you can see, this is data from 1930s. And this was actually, data was used by Ronald Fisher, who is one of the big guys in the early days of statistics, and he used this data in his 1930s book. But no one noticed that this thing was happening with Morris. And trellis plots made it obvious that that was happening. Also, these trellis plots allow you to compare from one location to the next. So we can see Grand Rapids has typically the smallest yields. Now, what makes this story even more interesting, at least for those of you who are awake right now, what makes this story even more interesting is that just very recently, within the last few years, someone examined the data in Morris, and while we see here, hey, this is interesting that Morris is reversed from the rest, but they actually went, I think they actually went back to the original data, and they found out that simply in the data numbering, the years were actually accidentally switched, so that Morris actually follows the same pattern as everyone else. So, a little story. And lastly, there's a nice little reference on ODS graphics. Okay. So that's the end of the graphics section. Are there any questions? Let's move on to the data step section. Okay. So what we've seen here with data steps, we've had some very basic uses of it. It allows you to, for example, it allows you to do stuff with data in terms of not necessarily doing like a formal statistical analysis, like estimating a regression model, but instead allows you to get data into SAS. It allows you to make small changes to the data sets, like what we saw with the serial data. But the data set can do a lot, do that kind of stuff, but on a bigger scale. And so what we're going to spend some time now is talking about some of the finer points of using a data step. So first of all, early on in the semester, we talked about how, go back up, over here in the Explorer window, I said when SAS gets a data set that it can use, it puts it into a library. And this library is actually a physical location on your hard drive. And to see the data sets that I've read in and I've done stuff with so far here today, I can click on Libraries, and I can come here to Work, and here are the data sets that I've been working with. Okay? Now what happens again to all the stuff that's in the Work library when I exit SAS? It gets deleted. But let's say that you want to save a data set, a SAS data set. You know, this can be useful, for example, if you are using a lot of data sets to try to get the data set into a form that you can use with a prompt. I've saved SAS data sets in the past, for example, when I've done a research paper and I wanted to have an easy way to distribute a SAS data set that's used with a SAS program that I'm disseminating to others. So how can I save one of these SAS data sets? Well, that's where you can set up your own library. Okay. So we're going to work with the serial data here. To set up your own library, you just simply use the statement libname outside of a data step. And all this is doing is simply creating a name that's going to point to a particular location on your hard drive. So I decided to call my library Chris, for the lack of a better name, and it's going to be pointing to my UNL folder on my hard drive. So when I run this code then, what's going to happen is if I come over here to Explore and go up, you now see a library called Chris. Next, I like to put a data set into my Chris library. The way you do that is now with a data step, where you say data, Chris, the name of the library, dot the name of the actual data set. Let's say I want to call it set 1. I could have called it something else. It doesn't matter. And what is this data set based upon? Well, let's say I just simply take my previous set 1 that I've already had, which contains the adjusted serial data, and suppose I use that. So if I run this, and let me just show you that indeed I could have used some other name. I'm going to run this again. I come over to my library, and here you can see set 1 and this weird name data set that I just created as well. These are actual data sets that are stored now on my hard drive. Just to prove it to you in case you were doubting me. Yeah, they are right there. These will not go away when I close out SAS. I would have to actually delete them if I wanted them to go away. Now note that these are separate files in comparison to the same set 1 that we've had previously in the work library. These are separate files. So essentially I have this data set now stored in three different files on my hard drive right now. 1 in work and 2 in the Chris library. So that's how you can create a permanent SAS data set. Now you will notice, since I always like to see what the file extensions are, I always turn that on my computer. Notice the extension, a SAS7B DAT file. That's the file extension. Why? It's a SAS data set, DAT for data. 7B corresponds to the version of SAS when this first data file format came about in the mid-1990s. SAS was at version 7 then. So that's why it has that extension there. Any questions? Okay, let's next move on to the bottom of page 2. Let's talk about conditional execution. So in any kind of programming language, you're going to have the ability to, let's say, run some code if and only if a particular condition is satisfied. This can be very useful in programming. And very often the syntax is something like, if a condition is true, then do something. And then sometimes, depending upon what your goals are, you might also have else. So if that condition is not true, else do something else. Well, in a data step, we have the ability to use an if-then-else format too. So to give you an example where this can be useful is that we're going to go back to my place-kicking data example. There we go. Now come on. Here we go. Just clear some stuff out here. Okay. So as I mentioned to you with the place-kicking data set, I actually entered that in myself. It took me about 40 hours to actually go through a stack of play-by-play descriptions in the NFL during this particular season. I had a stack of papers about that high. I took my winter break, took about 40 hours, went through every single page of these printed off play-by-play descriptions, and I actually recorded, well, what did a field goal occur, did a PAT occur, what was the wind speed at the time, what was the score of the game at the time, what was the distance of the kick, and so on. That's how I spent one winter break. And after I entered that in, and this occurs in many other examples, that's why I'm telling you the story, is that the data is still not in the right form that I want in order to do my analysis. So I need to make some changes to the data so I can get it in the form so I can, in the end, estimate what's called a logistic regression model. And so to get the data in the correct format, what I actually did was I used a data step. I used some if-then-else statements in SAS to get the data in the correct format. And so we're going to talk about some of the things I did here. Now, the place-kick data set that I have, that I'm using here, is different from the one I showed you in a previous class. The one I showed you in the previous class was essentially after I got the data in a good format. The one I'm giving you here is more, you could say, the raw format in terms of when I entered it in. And so let me import that data set. I'm going to print the first few lines of it, and this is what we got. So the date for September 3rd, 1995, week 1. Location was New England. Time was 1 o'clock Eastern Standard Time. The type of the field, it was an outdoor stadium, or type of stadium was outdoor stadium. The field was grass. Temperature was 73 degrees. Humidity 64. The wind was out of the south at 11 miles per hour. No wind chill was given to me. It was sunny in terms of the cloudiness. The kicker was someone by the name of Barr. He played for New England. The opponent was Cleveland. It was good, the kick was. It was a field goal at a distance of 21 yards and so on. A lot of information that I recorded. So the first thing that we're going to do is talk about a simple case, and that is field. So field tells me, was it grass? I called it G. Or was it artificial turf? I called it T. Now, can you actually do mathematical calculations on something that has letters of G and T? No, you need to change them to mathematical values. So simply, I want this to be a 1 if it's a G, a 0 if it's a T. If then else. So, in my data step, my data that I read in from proc import was placekick 1. I'm going to create a new data set based upon it called placekick 2. And I'm going to say if field is equal to G, then for all those observations, create a new variable called field 1 and set it to a value of 1. Notice the semicolon. I'm not done, though. Else, field 1 is equal to 0, semicolon. So notice you cannot do this like that. You cannot. You have to actually do it this way. Why? Well, because I could have actually run this code without an else. In the end, there would be some 1s. What do you think the other values would be? Excuse me? No. You wouldn't be, are you saying like T? or whatever else field was, it wouldn't be that field.
Would it be missing value?
Missing value, exactly. It would be a period. Try it, see it. Okay. So that's my first if then else. This is pretty much about the simplest that you can get. Again, pay attention to the syntax. Let's take a look at the next one. The next one helps me determine, is the kicker kicking at his home stadium or is it at an opponent's stadium? Why is that important? Well, if it's the home stadium, that kicker's used to kicking there. His probability of success might be higher. He's used to the field conditions. He's used of you know, how wind typically is in the stadium and stuff. And so I need to come up with a binary variable that helps me determine, is the kicker from, is this his home stadium that he kicks in most of the year, or is it at his opponent's stadium? So in the data set itself, then I have location. And, you know, understanding, you know, for the purpose of this class, understanding what NE means is not important, but it means it's kicked at the New England Patriots Stadium. And if I move over to here for team, this tells me what team that kicker's on. New England. Ah, so that means that this was kicked at the home stadium. Look at the third observation here. Location, New England. The team, CL for Cleveland. That means for that person, this was at the opponent's stadium, and so this would be referred to as an away game, an away kick. So how can I get SAS then to correctly denote this? Well, if loc equal team, then home is equal to 1. Else, home is equal to 0. Okay. Let's go down to the next one. This one deals with wind speed. You know, intuitively, you know, if the wind is blowing against the ball as it's traveling to the uprights, you might expect that's going to affect the probability of success. So I need to somehow take that into account, or at least I want to take that into account when I construct the model. But I have a variable in my data set called speed. Let's take a look at it. And this gives me the wind speed in miles per hour. So you can see the first 4 observations were at New England. And this is actually the wind speed at when the game started. It was 11 miles per hour. But take a look at this. I have a little period there. That means it's missing for the next observation. This is now for a game that's in IN or Indianapolis. For football fans, why do you think that was missing?
They play inside.
They play inside. Exactly. Is there no wind speed inside? Well, you're inside. But is the air circulating? Yeah, it is. So for all the NFL teams that played in dome stadiums, I had missing values, except for one, in Detroit. It would always tell me the wind speed inside the dome stadium itself was something like 1 or 2 miles per hour. For baseball fans, if you remember the Minnesota Twins, when they used to play in the Metrodome, you know, it was kind of a legend. We don't know if this actually occurred or not. But there was a legend that when the opposing team would come up to bat, they would either turn on or turn off the air conditioner, because that air conditioner is blowing, you know, cool air, and it's producing wind. And I don't remember exactly what it was, if they turned it on or turned it off. But again, you know, if there's some kind of circulation of wind blowing, you might be thinking as the baseball is going up in the air, it's going to hit the baseball and cause it to either, not go as far or maybe even go farther, depending upon the direction of the air being blown. So because of that, I wasn't comfortable saying if speed was a dot, calling that a 0. So I had to come up with a different way to handle it. So what I decided to do was, well, you know, if the wind speed's 5 miles per hour, is that really going to affect the football? Probably not that much. If it's 10 miles per hour, maybe. And so what I decided to do was come up with a cutoff to say windy versus not windy. It's not perfect, but it seemed reasonable, a reasonable approach. And so I chose 15 miles per hour as my cutoff. How did I choose that? Well, I just simply look at the distribution of the wind speeds, and about the 90th percentile was 15. Again, it's not a perfect process, but there is a perfect process here. And so what I need to do now next, we're at 120 here, but I want to finish this data step. So what I want to do next then is say, okay, if it's an outdoor stadium and the wind speed is greater than 15 miles per hour, then I'm going to say it is windy. In other words, wind is equal to 1. Else, wind is equal to 0. I put that there as well. Maybe I didn't really need it, because as I told you, all the dome stadiums do have simply missing values, except for one, which was Detroit, which usually had a miles per hour of 2. But I guess just to be safe, I say, okay, if it's greater than, I'm sorry, if it is an outdoor stadium, that's the only time where I'm going to really say it's going to be windy. And so that's how I approached it. Now notice I have 2 conditions there. And the way to incorporate those 2 conditions is with the word and. There might be times where you want to do a or as well. And in fact, you could use an or, not for this example, but in other cases, if you want a particular value, only when at least one happens, you could do an or. You can have as many and ors there as you want in terms of different conditions. And you can use parentheses to help separate out different ands or ors to be evaluated. And so I give an example in the notes that I want you to look at on your own on page 5 and 6 after this class. It was just a made-up example. Okay. So now, let me run this code. And then I'm going to print. And of course, after you do a bunch of if, then, else's, you want to make sure, did it work out? And we can just simply check, for example, for field 1 here, first 4 observations were G's. I got a 1. Next observations were turfs. I got a 0. You can check the other ones too, and they do work out. Now, there may be times, though, where you are concerned. Well, in this example, since I entered the data and I thoroughly looked at it, I know that every single observation is either a G or T. I know that. But let's say you don't know that. And so to be a little bit more safer, you could watch out for other things that could happen. So for example, here is a set of nested if-then else's. So if field is equal to G, then I'm going to create a new variable called field 2. It's going to be equal to 1. Else, if field is equal to a T, then field 2 is equal to 0. Then another else. Notice how I indent everything. Again, you don't have to. It's not required in SAS, but it makes it a lot more readable. And then else, if anything else happens, let's call field 2 equal dot for missing. Let's say, for example, I forgot to put G or T. Or let's say I accidentally, since H, the key for H is next to G on my keyboard, maybe I accidentally hit H instead. And so this will help me double check things. Help me make sure that I did get it right. And so then when I actually, let's say, do some checks afterwards, such as this right here, I do a proc freak with my new data set. Let's look at field versus field 1. I know I could use field 2 up there since that was my example. Notice everything is like what it should be. All the 1s and the 0s correspond to the right G's and T's. It's essential to always do checks like that. Okay, let's see here. So let's go to page 6, and we'll be done very shortly here. I think, yeah. So we basically got up to here. It's going to take me a while to explain the next thing right there. So we'll just end it there. Are there any questions? Okay, that's it for today.